Hi everyone and welcome back to PrepFusion. I'm Anish and today we will start with the lecture 58 of our machines chapter, that is uh, starting of synchronous motor, right? Starting of synchronous motor we will discuss. Also we will discuss briefly about voltage regulation. Okay, so let's discuss, like previously also I have mentioned, starting it is not self starting. I have also told you why, because the average torque is zero. Let's try to get more deeper into it, right? So we know that the stator magnetic field will rotate, the poles of the stator magnetic field will rotate at a speed ns, that is 120 f by p, right? So what is the speed of the stator magnetic field? If let's say f is 50 hertz, okay, and number of poles, let's say is, I can take a considerable amount of uh, pole, let's say number of poles is 2, okay. So this will be what, then my ns will be 3000 rpm, correct? Ns will be 3000 rpm. Revolution, this many number of revolutions it is doing per minute. What is the revolution per second? Ns, this divided by 60, right? Per minute it is doing 3000, this divided by 60 will give me 500. Am I correct? Yes, 500, or no, 50 only, 50. Yeah, 50. So it is doing 50 revolutions per second. In a second it is revolving 50 revolutions, and the rotor will have its own inertia, right? Initially rotor is stationary, and what do you know? We know that alignment torque acts between the rotor and the stator. Alignment torque acts between the rotor and the stator, that is what we know, right? But what is the problem over here is that this stator magnetic field is rotating so fast that it is not able to align, because the average torque is zero, because initially here north pole was here, right? Then it was giving repulsive torque here, north pole came in a split of seconds, in a very short duration. North pole again came here, then it is providing attraction pole to the same rotor. At an instant it is providing repulsion and attraction force. So overall the average torque will be zero. That's why it is not inherently self-starting. Same thing, whatever I have discussed is written over here. Basically what will happen, the rotor vibrates or remains still, cannot lock into synchronism with the stator field. Hence synchronous motor are not self-starting. Okay, that is the main thing, right? So how can I make it self-starting? By using damper winding. So this already we have discussed that we can use damper winding. It helps in hunting as well as making in starting, because the more there is relative speed between the stator field and the rotor, damper winding will induce a current that will induce a torque, so that the motor becomes self-starting. So that is why damper winding is used. Okay. So what we know is, we know one thing, right? We know one thing, that if I want to increase my starting torque, how will I increase my starting torque? How will I increase my starting torque? So we know the slip, right? This torque slip characteristics is with respect to induction motor. So the starting of synchronous machine starting of synchronous machine will behave as induction motor. And I know one thing, this formula, the slip at maximum torque. What is the slip at maximum torque? It is, if you remember, it was R2 upon X2. This is the slip at maximum torque, and this position is what, this is slip equals to 1, because here my rotor is stationary, rotor speed is 0. So I want the maximum torque to happen at stationary. So I want to shift this graph to the left hand side. How can I bring it to the left hand side? So as I move on the right hand side, slip reduces. So I want the maximum slip to happen at the starting. So I want to increase my SM to higher value. That's why we want to increase the rotor resistance R2. If I increase my rotor resistance R2, that is how my slip at maximum torque will increase. Hence I will get the maximum torque at the starting. So that is the reason why we make our damper windings high resistance. In the previous lecture also I mentioned. So here I hope it is more clear why we want to increase the damper winding resistance. Okay. So I hope it is clear, right? What is damper winding we already know, so I don't think we have to explain it over again. So that's it. This is how the motor will start. Okay, so at the instant of startup, the rotor is stationary while the stator's rotating magnetic field rotates with speed ns. This relative motion induces an emf in the damper bars, which causes circulating current to flow. According to Lenz's law, the induced currents produce a torque that will oppose the relative motion, thereby pulling the rotor in the direction of the stator's magnetic field, just like an induction motor. The rotor begins to accelerate and approaches synchronous speed. Okay, so because it wants to reduce the relative speed. Once the rotor gets close to ns, the dc excitation is applied to the rotor field. So dc excitation is not initially applied. So very important point, dc excitation is not applied initially. So what we do is, at starting, the starting behavior of synchronous machine and induction machine will be same, because if I don't provide any dc excitation, it is just a induction machine, right? So starting behavior of synchronous machine and induction machine is same. Okay, that is what the starting behavior of synchronous and induction machine. Okay, and during running, what do you do? Initially, as my nr reaches closer towards ns, then I provide dc excitation, then this locking will work. Then the stator magnetic field and the rotor magnetic field will be able to lock, because it is very near, right? So it will be able to lock. So once close to ns, the dc excitation is applied to the rotor field winding. The rotor magnetic field synchronizes with the stator's rotating magnetic field, and the motor continues to run at constant speed. Okay, so nr becomes ns. After synchronism, once the synchronism is achieved, relative motion cases and the induced emf in the damper winding drops to zero, because there is no relative motion between the rotor and the stator magnetic field. That's why the induced emf will be zero. Hence, the damper winding becomes inactive and torque is not developed fully due to the synchronous interaction of the stator and the rotor magnetic field. So now let's discuss about, okay, a few other things are there. So behavior of loss of excitation. If the field excitation fails during operation, the machine can temporarily continue running as a induction motor. Okay, utilizing the damper windings. So basically, if let's say my field windings, right, are not providing current, so there is no pole, north pole, south pole in field windings. So due to the presence of damper bars, temporarily my synchronous machine can work as an induction motor. Temporarily, okay, it can work as an induction motor. However, prolonged operation without excitation is inefficient. Like efficiency will not be good, because I have developed my machine, I have constructed my machine keeping this in mind that it's a synchronous machine, not a induction machine, right? So that is the problem, and that may damage the machine due to heating or unstable operation. Okay, that's can damage. So longer duration of operation is not suited, but for shorter durations it is totally fine, we can use it. Okay, so for higher starting torque, damper windings should have moderately high resistance. Already explained the reasoning behind why it should have high resistance. Okay, now let's discuss about a test known as slip test. So slip test is used to measure basically the uh, xd, that is the direct axis synchronous reactance, and the xq, that is the quadrature axis synchronous reactance. Okay, we want to measure the xd and xq. How will you measure the xd and xq? So what we do is, we use this, like we know that according to Blondel's two reaction theory, there will be two reactants. One will be direct axis. So where is the picture? So here, right? So there will be two reactances. So we'll copy this. There will be two reactants, right? One will be along the direct axis, this will be one of the reactants, and one will be perpendicular. Now, if I do one thing, that let's say I am not providing any rotor current, okay, and I am keeping the rotor stationary, or let's say I am moving the rotor by external means. If I am moving the rotor by external means, one thing is for sure, let's say I am measuring, like through the stator winding, right, I am measuring the current and the voltage. I'm measuring the voltage and the current. Okay. So if I'm measuring the voltage and the current, if the rotor is in this position, what will happen? Can you tell me what will happen if the rotor is in here? So if I'm measuring the voltage and current, right, in this, what will it measure? It will measure the XD, right? The ratio of voltage by current, it will measure XD, voltage by current, right? If my rotor is in this position, if my rotor, or okay, let me do one thing. Now, okay, let me do this, right? Let me rotate this. If my rotor is rotated, now if I measure the current and voltage, then what will I measure now? Voltage to current. So this, right, this is what? Higher reluctance. So now I will measure the XQ, V by I. So this is exactly what we will do, is we will do one thing, that we will provide a three-phase balance supply on the stator side, okay, and we will provide a ammeter and voltmeter, and that ammeter and voltmeter will not measure the average value, RMS value, they will measure the instantaneous value. Instantaneous, we will do instantaneous reading, instantaneous reading, okay. So what we will do is, when the rotor is here, then the reluctance will be minimum. If the reluctance is minimum, then the current will be maximum, right? Because it is a ratio of what? Sorry, what I'm saying. It is XD, and we know that XD is higher than XQ. That we know, that we have already discussed. If XD is higher than XQ, then this voltage will be maximum and current will be minimum. When the rotor will be in this position, voltage will be maximum and the current will be minimum. When the rotor is in quadrature position, voltage will be minimum, current will be maximum. Okay. So we will measure the instantaneous value, and if I take the ratio of these two, I will be able to get my XD and XQ. That's it. Okay. So the slip test is essential experimental procedure used to determine the direct axis reactance and the quadrature axis in salient pole machines. So the salient pole machines, the magnetic reluctance varies along the D and the Q axis when the rotor is slowly rotated. So there is a slip between the rotor speed and the stator. So that's why the slip, the term slip came, right? Slip test, because there is a slip between the rotor, because I am rotating the rotor. Okay, the rotor field poles alternately align with the D axis and the Q axis relative to the stator MMF, right? So because initially rotor field poles is in the north pole, sorry, in the D axis, here it is in the Q axis, right? If it is in the Q axis, then the reluctance will be higher, here the reluctance will be minimum. So if reluctance is minimum, then the reactance also will change, and accordingly the ratio also will change. So field winding, we keep it open circuited, so there is no possibility of current flowing through the field winding. A low voltage three phase balanced AC supply is applied to the stator terminals. So we apply a low voltage three phase balanced supply. The rotor is drawn by a external prime mover at a speed slightly less than the synchronous speed. Okay, so it is slightly less than the synchronous speed, but still it is good speed. So slip will be very small. Slip is what? Ns minus Nr divided by Ns. Okay, so of course if Ns minus Nr is very small, right, because Nr is very near to Ns, so slip also will be very small. The stator line voltage and current waveforms are recorded using an oscilloscope data. So they will be recorded using the oscilloscope, and we will always take the ratio. What ratio? We will take the ratio of V maximum and V minimum. So basically the connection diagram, where is the connection diagram? Okay, I don't have the connection diagram. Okay, yeah, here is the connection diagram. So I will see the graph, and from the graph, wherever I will see that my voltage is maximum, okay, V maximum, and of course it is line voltage, it is star connected, so it will be V maximum by root 3 divided by the minimum current, that will be my XD, okay, from the graph, okay, and from the same graph, the minimum voltage and the maximum current will give me XQ. Okay, this is the minimum voltage and maximum current, this is the maximum voltage and minimum current. Okay, so that is the case. Okay, so yeah, that is how what we will do. So when the rotor poles align with the stator poles, that is here, okay, that is here, then the reluctance is minimum. So here, let's say the rotor poles are here, rotor poles are here north and south, and let's say stator poles is also here north, sorry, this will be south, this will be north. So if the rotor poles and the stator poles both are aligned, then what reactance I will get? XD, right? So that's why it is telling then the reluctance will be minimum, because the reluctance between the north and south is minimum. Then there will be maximum impedance, basically there will be maximum reactance, right? X. So current will be minimum, and voltage I will get peak voltage. So the voltage will have a peaky nature. Okay. So this is the point of direct axis. So this will be the direct axis. And when, let's say, my rotor poles are in the same position and my stator poles are here and here, so it is in the quadrature axis. So here if I see the link up, right, between the stator north pole and the rotor south pole will be like, it will have highest reluctance, it will have highest reluctance. So reluctance will be maximum, so impedance will be minimum, okay, maximum current, and valley voltage, meaning voltage will be like a valley, like this, voltage will be minima, current will be maximum, hence the impedance will be minimum. Okay, Z impedance will be minimum. Okay, so I hope you have understood. So that's it. Just understand what is slip test, what we do, that's it. That is only important for you. Okay, so this test does not require any synchronization, since the rotor is driven externally. It must perform at a low voltage and no load to avoid heating and damage, because we don't want to damage the windings, because if I provide high voltage, then the windings can get damaged if some high current flows. Okay, the name slip test originates from the fact that the rotor is operated at a slip speed with respect to the stator's rotating magnetic field. We manually externally operate it at a different speed. Okay, so yeah, these are the few cases. So main application is to calculate the XD and XQ. That's it. That's it. Okay, so let's solve a question according to this. During slip test conducted on a salient pole synchronous machine, the direct axis and the quadrature axis reactance, following readings were recorded. Maximum current was this, minimum current was this, maximum applied voltage was this, minimum voltage was applied this. Okay, remember, whenever nothing is mentioned, you will assume that your stator star connected. Okay, assume your stator is star connected. If your stator is star connected, I have to find out XD. XD will be what? XD, remember this thing, already we have discussed, XD is generally higher than XQ. So XD will be V max by root 3 by I minimum, and your XQ will be V minimum by root 3 by I minimum. Okay, so this will be XT will be equals to V max. What is V max? V max, if you see 30 volt, and I minimum is 6.5. So 30, nothing is mentioned, they are measuring the line voltage only, divided by root 3 divided by 6.5. So this value will be 30 divided by root 3 divided by 6.5. So X D comes out to be 2.665 ohms. Okay, so XD comes out to be 2.665 ohms. That is actually present nowhere. That is interesting. I think option framing kind of somewhere we missed the mark or something. Huh? Okay. No. Actually, what they did, actually, they should have mentioned that it is delta connected. Yeah, because yeah, if I multiply this by root 3, right, then I think some of the option will get matched. Yes. Okay. So I should have mentioned it. Stated. If nothing is mentioned, you will assume it to be line connected, but I will say stator is delta connected. I will write somewhere stator. Where would I write? Here only I will write stator right here. Stator delta connected. But here they have told it is delta connected, so I will not assume this, right, because it is already mentioned. If nothing is mentioned, so this I will use when if nothing is mentioned. So I don't need to divide by root 3. So this will be 4.66 ohms. Okay, and xq equals to V minimum by V maximum, I maximum. So V minimum is 25, I maximum is 10. So it will be 25 divided by 10. So it will be 2.5 ohms. Okay, this will be my xq. So xq is 2.5 and xt is 4.615. This will be option B will be the correct answer for this question. Okay, so now let's start with another topic, that is voltage regulation. What is voltage regulation? So voltage regulation, already throughout machines we have discussed, it is the no load voltage upon full load voltage divided by the full load voltage. That is the simple formula. So what we know, what is no load voltage? No load, like if it is a alternator, right, what will be the no load voltage? Basically this is my EF, right, or E, whatever you want to write. So no load voltage, this is my JXS. Okay, so this is my voltage at the terminals. So no load voltage will be when I is equals to 0. When I is equals to 0, V is equals to E. So basically the formula for voltage regulation becomes E minus Vt divided by Vt into 100. That's it. Because at full load, some IA current will flow and I will get the full load voltage, that is Vt. So we get this voltage regulation, right? One more thing I know, that for leading load, for lagging load, right? For lagging load, I know that magnitude. So this will be magnitude, right? Because of course they will have phase quantities, but I am talking about magnitude. So I know for lagging load, magnitude of E is always greater, has to be always greater than magnitude of Vt, already have been proved. Okay, these all things have been proved. So that means my voltage regulation will be positive. For leading load, the voltage regulation can be negative because the magnitude of E can be lower than Vt. Okay, this case we have done, I have proven it to you. So voltage regulation can be negative, not always, it can go negative. Okay, these are few important things to understand. So for lagging load, for inductive load, the induced EMF will always be higher. So voltage regulation will be positive. For leading load, it will be capacitive. For capacitive load, voltage regulation can become negative. Okay, there can be a negative case. Okay, so obviously for ideal case, okay, leading power factor already we have done, right? For unity power factor, armature reaction is cross magnetizing. Again, voltage drop is moderate. Voltage regulation will be slightly positive. Okay, so machine with higher synchronous reactance obviously will have higher voltage drop. That's why the voltage regulation also will be high, because the difference between the voltages will be high. Because what is the drop? Drop is I into excess. Higher the excess, higher the drop. Okay. In power system, negative voltage regulation can help in improving the voltage profile. This we will see in the power system. So voltage regulation basically gives us the how much stable my voltage is. Okay, with change in current. If I change my current, how much stable my voltage will be at the terminals. That is the parameter that voltage regulation gives me. Okay, that is why voltage regulation is very important to us. So let's solve this question, a very basic question on voltage regulation, and after that in the next lecture we will understand few more parameters like open and short circuit parameters. Also we will see the different methods of voltage regulation, right? What are the different methods of voltage regulation? Actually there is only one, other things are theoretical ones. Okay, mainly we use one method. So let's solve these questions. So an star connected alternator rated at 440 volts, so its no load full load voltage is 440. So here VFL is 440. It is star connected, so I will obviously write per phase voltage. So per phase will be 440 divided by root 3. And synchronous reactance per phase is 10 ohms. Okay, synchronous reactance per phase is 10 ohms. It is supplying a balanced capacitive load drawing 20 ampere per phase. Okay, so a balanced capacitive load is connected, right? Balanced capacitive load that is taking 20 amperes. So magnitude of IA is 20 amperes. It is a capacitive load but not purely capacitive load. Okay, it is a capacitive load but not purely capacitive. I don't know about the angle. As represented in the per phase equivalent circuit, to achieve zero voltage regulation under this condition. So we want to achieve zero voltage regulation. So my voltage regulation will be zero. It is a leading power factor. So I want my, how will voltage regulation be zero? It is basically magnitude of E minus magnitude of V full load divided by magnitude of V into 100, right? So this has to go to zero. That is my magnitude of E has to be equals to magnitude of V. When is it possible? So for leading load, do you remember how it can be higher? How my magnitude of V can be higher than magnitude of E? So if you remember the formula for magnitude of E, right? In case of a leading load, this you have to remember. It was V cos theta. Here I had minus IRA. Remember there is no resistance here. Okay, so not minus IRA, plus IRA, because of course E will be addition of this drop, right? So plus IRA whole square plus V sin theta minus IA XS. If you remember, this was the formula, right? Okay. Okay. So I know what is like here, right? Magnitude of IA is there. RA is 0. I know what is IA. I know what is XS. Do I know theta? No, I don't know theta, but that is what I have to find out, because they are asking me what should be the power factor of the load. So basically I know E, right? What is magnitude of E? Magnitude of E is same as V. It should be this value only. So basically this should be equals to V. So I will square both sides. This will be V square. This will be V square cos square theta plus RA is 0. So it will be V square sin square theta minus 2 V IA sin theta into XS. uh, plus ia square xs square, right? So basically this, right, is what? V square sin square theta plus cos square theta, which will be v square only. So v square will get cancelled. So I will get this value. So I will get my v via. So ia will get cancelled. Basically sin theta will be equals to ia square xs square. So sin theta will be equals to ia xs square divided by 2v. Okay, so from here I will be able to find out the value of sin theta. So I know what is ia. Ia is given to me, that is 20 amperes, right? Xs is how much value? Synchronous reactance is 10 ohms, correct? Whole square divided by 2 into v. V is 440 divided by root 3. So from here easily I will be able to find out the sin theta, and from here I will be able to find out the power factor of the load. It is actually a gate question. Okay, so this will be 20 into 100 divided by 2 into 440 into root 3. Okay, what is happening? It is more than 1. How is it possible? Am I messing up something? Oh, sorry. This is, here I have excess, right? So one of the excess also will get cancelled. Sorry. Okay, this will get cancelled. So this will not be 100 square. That is what I was missing. Divide by 10. So point 39367, and if I take the sine inverse, so here theta is 23.18167. Okay, theta is 23.18167. If I do cos of this, cos theta will come out to be 0.919. Okay, and it will be leading 0.919, and it will be leading. Okay, so this will be the answer. Power factor will be 0.919, and it will be leading. That's it. Now let's solve the next question. This is another question, like similar kind of question. An alternator with synchronous, like why it is leading, I hope you remember, right? Because it is a capacitive load. That's why. An alternator with synchronous reactance 20%. So excess is 20%, or in per unit it will be 0.2 pu. Negligible armature resistance delivers its rated current at a certain leading power factor. So it is a leading power factor such that the voltage regulation is 0. What is the value of the leading power factor? So it is delivering rated voltage at leading power factor. Okay, so rated current means ia will be, in per unit it will be 1 pu. What will be voltage? Full load voltage. Full load voltage will be 1 pu. And what will be e? E also will be equals to magnitude of v, because your voltage regulation is 0. Same question, right? Same question. So again I can use the same formula, exact same formula. I have to find out power factor, right? So I can write the same formula, that magnitude of E is equals to V cos theta plus IA I whole square plus V sin theta minus IA excess whole square. So everything is in per unit. Remember, everything is in per unit. So this will be E square. So this is E square, means it is 1 only, equals to V square minus 2 IA V excess sin theta plus IA excess I square x square. Okay, so this will be one square into 2 into 1 into 1. Excess is how much? Excess is 0.2 into sine theta plus ia square 1 square into 1 xpu is also 1 only. Oh sorry, 0.2 square, right? Okay, anyways this 0.2 will get cancelled. Okay, so what we will be left with is sine theta will be equals to 0.2 divided by 2. So it is 0.1 basically. This will go on that side. 0.2 by 2 will get cancelled. Sine theta will be equals to, yeah, 0.1. Sine theta will be 0.1. So what will be my cos theta? Because they have asked the power factor. So power factor cos theta 0.1 sine inverse cos of this, it is 0.995. Okay, very near to 1 only, unity only. So it is 0.995 leading. Okay, so the power factor will be 0.995 leading if the per unit values are given as such. Okay, so I hope this question is clear to you, not that difficult. Just the difference is here it is per unit, previously everything was actual value. Okay, that is the difference. So with this we end our lecture basically. So this lecture has been ended. In the next lecture we will discuss about open circuit and short circuit characteristics, short circuit ratio, and different methods of voltage regulation, calculation of voltage regulation. Thank you, and I will see you in the next lecture. Until then, happy learning.